Hello everyone, thank you for watching the video of my talk. Today I'll be presenting work with my advisors, Siva, Theja, Maguluri, and the title of our work is Load Balancing System under JSQ and Power-of-d, Managed Server Heavy Traffic Asymptotics. In our daily life, we interact with different systems where we might be a server or we might be a client or a customer that needs to wait in line until our request can be processed. Here are some examples. For example, this is a toll in a highway. There are call centers, ride-sharing apps, delivery apps, or basically anything related to the cloud involves this process. And the ultimate goal of my research is to minimize delay in these systems. Today, we will be looking at very large systems, such as a data center, for example, where the number of servers is huge. And the goal is to understand delay behavior in a load balancing system. So the outline for the rest of this talk is here. We will start defining the model, then we will move into defining the asymptotic regime we will be looking at. We will present the result, and then we will discuss some conclusions and future work directions. Let's start with the model. We will look at a load balancing system in discrete time, meaning that we will be looking at time slots or time windows. There are n servers, and each server has an infinite buffer. The number of jobs at the beginning of time slot k in Qi will be denoted by Qik. The arrivals to the system occur in a single stream, and we will denote them by A of k, which will be a sequence of IID random variables. And then after arrivals, a router has to decide where to send the arrivals of each time slot. There is also a service process. Each server can potentially process Si of k jobs in each time slot. And I say potential because we want the service process to be independent of the queue length. So if there are less jobs than the potential service, then we just process the number of jobs in the queue. Routing will occur according to Power-of-d choices. What is this? Well, we have to fix a number d between 1 and n, an integer number. The first step whenever there is an arrival is to select these servers uniformly at random, and then we will route all the arrivals to the shortest queue among those d that we selected in the first step. So for example, if d equals 2 and we have 3 arrivals in time slot k, we select 2 queues at random, in this case queues 1 and 3, and we send our arrivals to the shortest queue among those. So observe that in this case, all the arrivals go to the first queue, even though the second queue was shorter. Some observations. This algorithm is also known as JSQD, where JSQ stands for join the shortest queue. If d equals n, then we're looking at the classical JSQ algorithm. So the arrivals will go always to the shortest queue among all. And if d equals 1, well, if d equals 1, step 2 is not doing anything basically. So d equals 1 implies random routing. This completes the definition of the model. Now let's step into the asymptotic regime we will be looking at. So I said before we have n servers, we will assume the service rate of each of them is equal to 1. And we will parameterize the arrivals with respect to n as follows. We will take a number alpha, which is greater than 0, and we will let the expected arrival rate, the expected total arrival rate be n times 1 minus n power minus alpha. And observe that this means that the arrival rate per server will be 1 minus n power minus alpha. Then we take the limit as n goes to infinity, which implies that the number of servers go to infinity and that the difference between the service rate and arrival rate of each server will be going to 0. Of course, we are not the first ones to look at this regime. Depending on the value of alpha, there's great amount of literature. And as alpha goes to infinity, we are intuitively approaching the mean flow regime. As alpha goes to infinity, we're intuitively approaching the classical heavy traffic regimes. And if alpha is a finite value, we know there are phase transitions at alpha equals half and alpha equals 1. And most of the literature is for alpha between 0 and 1, but in this talk, we will be focusing on finite values of alpha, which are strictly greater than 1. Some related work is by Zua and Schroff, but their approach is a bit different because they are looking at a large number of routing algorithms, whereas we're focusing on power-of-d. So this completes the definition of our asymptotic regime. Now let's move to the result. So remember, we were focusing a bit on the service process. We said all the servers are equal. We will assume they are independent, and we will let sigma s squared be the variance of the potential service of each server. For the arrival process, we said before the expected number of arrivals per time slot will be n times 1 minus n power minus alpha, and we will let the variance of the arrivals in one time slot to grow linearly with n. In particular, we will assume the variance is equal to n times sigma a squared. This means that the arrivals per server will have mean 1 minus n power minus alpha and variance sigma a squared. Further, we will not assume that d is a parameter which is independent of n. We will allow it to be dependent on n in the following form. So d will equal c times n power beta, where c and beta are non-negative constants. And observe that if beta is equal to 0, then we're under the case where d is a fixed number. So our theorem says if alpha plus beta is greater than 11 halves, then we have that the scaled total queue length will converge in distribution to an exponential random variable, which depends on sigma a squared, and sigma s squared. And this is very similar to the asymptotic behavior in classical heavy traffic. In classical heavy traffic, we also have convergence in distribution to an exponential random variable. So the first thing to notice is that if we apply this result to JSQ, which means that beta equals 1, we get that if alpha is greater than 9 halves, then we have the convergence result. And as I said, the proof is very simple. We just set c and beta equal to 1 in the theorem. Now, how do we prove this theorem? Well, we have two proofs for the same result. The first proof involves the MGF method, which is a framework that we developed to study heavy traffic analysis of systems that satisfy the complete resource pooling or that have state space collapse into a one-dimensional subspace. And in this case, we first need to prove some notion of state space collapse. I put here some quotation marks. I will explain why later. And then we set to 0 the drift of the function that will give the moment generating function, and we follow the steps from this framework. The second proof uses Stein's method. And again, we have to prove a notion of state space collapse. It will happen that this notion will be same in both cases. And then the second step is to compute an upper bound for the Wasserstein distance between the queue length, the scale total queue length, and the exponential random variable of the limit. Then if that upper bound goes to 0, as n goes to infinity, we have the result. So what do I mean by state space collapse in quotation marks? Well, in heavy traffic, we know what's state space collapse. For the load balancing system under JSQ or under power-of-d choices, we project the vector of Q lengths on a line where everything is equal. So for example, if that's the vector of Q lengths, and this is the line where everything is equal, we define Q parallel as the projection and Q perp as the difference between the actual vector of Q lengths and Q parallel. And in heavy traffic, we say that Q can be approximated by Q parallel because we are able to prove that the norm of Q perp has bounded moments. And that implies that Q perp becomes negligible as we approach the heavy traffic regime. Why? Because the vector of Q length becomes larger, and since Q perp is bounded, then that means that Q becomes more and more similar to Q parallel. In this case, we have a similar result. We again find an upper bound for Q perp, for the norm of Q perp, but this doesn't really imply that Q and Q parallel are equal. And the reason why this is more complicated is because these vectors are becoming vectors with infinitely many elements. So in particular, what we prove is that the rth norm of the expected value of the norm of Q per power R and everything power 1 over R is upper bounded by this number right here. Here, C tilde is independent of R, N, and D. And then here we have R times N power 9/2 divided by D minus 1. Observe that this D minus 1 is important because when D equals 1, then we have random routing. And in that case, the space collapse doesn't hold. And well, then we use this result in the respective proofs with MGF method and Stein's method. And this is sufficient to show that Q perp is negligible. So that's why we call it state space collapse. Well, that concludes what I wanted to tell you about the proof. If you want to know more about the details, I'll be happy to discuss offline. But due to time constraints, I will not do it now. So now let's move to the conclusion and some future work directions. So what did we do today? We studied a load balancing system on the Power-of-d, and we looked at the many server heavy traffic regime. And we were looking for conditions on alpha such that the behavior of the total Q length is similar to the classical heavy traffic behavior. We showed that if D is a function of N defined by this expression here, then if alpha plus beta is greater than 11/2, then we observe the heavy traffic behavior. And in particular, for join the shortest Q, we get alpha greater than 9/2. So the main question for future work is, can we close the gap? Can we get alpha greater than 1? Because remember, in the literature review, people have been studying this many server heavy traffic regime for load balancing when alpha is between 0 and 1. So can we push these 9/2 in particular to 1? To answer that question, we know the bottleneck is our proof of state space collapse. So one question is, can we get a tighter bound? Or maybe there are other phase transitions. Maybe we cannot get to alpha greater than 1 because there is another phase transition, and for example, which implies that not for all alpha greater than 1, our system will behave as in heavy traffic. Also, a burning question is the following. So before I used the Power-of-d proof to conclude that for JSQ we need alpha greater than 9/2. However, if I follow the same two proofs with Stein's method or MGF method directly with JSQ and I exploit the properties of JSQ, we get alpha greater than 4, which is 1/2 away from this bound right here. And the question is why? We still don't know why, and it's something we are exploring. Well, that concludes my talk today. Thank you for listening to my video. I'll be happy to answer questions during our session or offline.